Thank you. Got it. Welcome back. It's the second day of our school, as we mentioned, and I'm going to talk about grazing incident X-ray diffraction. I would just call it GID. And the plan for this lecture is that we split into two parts. The first part will talk about 30 minutes, and then we'll leave you 15 minutes for assignment 1. And then after a break, I will talk for another 30 minutes, and then Wei is going to take over to for your assignment 2. So let's start with taking a set of X-ray data, diffraction data, of course, virtually. And you have a sample ready, which is a monolayer of gold nanoparticles in Langmuir trough, and you turn on the X-ray beam. The beam coming from the right, deflected by the steering crystal, down to your sample. And the diffraction pattern here is collected by this 2D detector rotated around the z-axis. You may notice that we don't rotate our samples during the scan, and that's because our sample is essentially polycrystalline or powders. And you can see from this TM, the green size is quite small. And if you have samples with large crystal domains, then you will need to rotate the samples as you do the scan. So here's the top view of this scan geometry. And a GID scan covers a range of detector angle theta with increments of a delta theta steps determined by the resolution you needed. For a GID scan, we use 2 pairs of slits tightly closed to define this scattering signal on the detector. So each of the data point actually is a 1D GID, meaning one QXY value and many, many QZ values here. So after you've done this, collecting a set of a GID 1D data, you combine them together by simply just place them next to one another. There's no patching and no scaling factors involved here. And with some image massage, we finally present you with this pretty 2D GID pattern. So now with this GID pattern in hand, and what kind of structure information we can get out of it. Specifically, given the pattern of the Bragg peaks along the QXY axis, what will be the 2D crystal structure at the interface? And the second is what are the Miller indices of the Bragg peaks? And third is what information can we obtain from the width of the peak here? And the fourth one is why the intensity of the diffraction peak modulated along the Q axis, and what kind of information we can get out from this intensity pattern. So if this is diffraction pattern for a monolayer of a DPPC, although it doesn't have that many diffraction peaks, it's equally rich in structure information. So all these 4 questions are still apply, but a 5th question is added. So why is there an outplane peak? So those questions set the goal for this lecture and exercise involved. That is, from the GID pattern to the crystal structure of the films at the interface. So the outline of this lecture is as follows. First, I would discuss the physics of X-ray diffraction, and then I will show you how to solve 2D crystal structures from the diffraction pattern. Then, following that, we will show how to determine the correlation length of the structure and the shape of the particles. So let's have some physics. So when the X-rays shine on an object, whose electron density distribution is R rho. We all know that X-rays sees electrons when they shine on an object. So the intensity that you observe on the detector is proportionally to the Fourier transform of this electron density squared. So now you see the intensity is described in the Q space, we're now familiar with already. For a periodical object, rho r, the electron density can be written as the individual particle function phi r convoluted with the distribution of those center of the particles, psi here. The convolution is given in this integration function here. So mathematically, the Fourier transfer of this convolution function is equal to the product of the Fourier transfer to the individual functions here. So now we have phi Fourier transform that's defined as a form factor, and the size Fourier transform squared, that's a structure factor. So with these expressions, we can relate the real electron density, a real space electron density function for your sample to the reciprocal space diffraction intensity functions now. Now the task is to see how we can describe the diffraction pattern using the structure factor and form factor. I'm not dealing with the mathematical functions. I just wanted to give you a sense what the structure factor does and what the form factor does. So first, a purely mathematical sample, a perfect 2D hexagonal crystal of dots. In real space, the phi is a dot, basically a delta function. And psi is the distribution to describe the packing of those dots. So in the reciprocal space, we've said that structure factor is the Fourier transform of this packing hexagons. So it just give you a very skinny diffraction peaks along QXY. And in the form factor, Fourier transform of a delta function give you a constant. So the form factor doesn't modulate, doesn't modify your structure factor at all, the diffraction at all. So this peak in the QXY position, it just doesn't change along the QZ direction. In fact, doesn't change in any direction. So the product, the intensity, which is the product of the form factor and structure factor, in this case, just a structure factor, it's just a bunch of skinny lines. And those lines are referred to as Bragg rods. Now we smash this perfect crystal in two pieces. So the sample now become a 2D polycrystalline array of hexagonally packed dots. So in real space, phi is still the delta function, but the psi is different now. So the Fourier transform of this psi function just basically broaden the same set of peaks. And I will deal with this. This has something to do with the correlation lens, and we'll talk about later. But the smaller the crystal, the broader the peak. And we already said the psi didn't change, the form factor is still a constant, so it doesn't do anything to the peak. So now the diffraction for this sets of data become a thicker bunch of lines. It's a Bragg rods. So now we got to a set of a real particle samples. So it's a 2D polycrystalline array of a close packed gold nanoparticles. And in real space, phi now, it's the core of one of the gold nanoparticles. It's a sphere. But its psi is the same, still polycrystalline. And so that means the structure factor didn't change. However, the form factor changed. it's this oscillation function, which will give you exactly what it looked like later. So this is in one QZ direction. In fact, this is also modulate the form factor modulate in the QXY direction also. So you can think of it as a sphere up to the first minimum here. It's a symmetric spheres all over Z direction and XY direction. So now I'll give you the real diffraction pattern. It looks like this. All the white lines here follow the minima of the form factors. So now you see the Bragg rod is modulated along Z directions. So now the last example is a lipid monolayer. And the lipids here are modeled as finite length, skinny, non-tilted cylinders in a 2D polycrystalline array. So the phi is now a finite length cylinder. Psi function is still the same as in the gold case, see 2D polycrystalline. So that means the structure factor didn't change. The only thing that changes, and I didn't plot any higher order peaks here because normally we don't see higher order peaks for lipids. And the form factor is different now. For QZ, it's modulated. QXY, not so much because we're talking about skinny cylinder. In fact, you can think of this form factor in 3D as a oblate ellipsoid. And in QZ direction, meaning this direction, it's a sinc function up to first minimum here. And QXY function, it's a Bessel function, basically it's a disk. I ignored all the other simulations. So for a non-tilted lipid system, you will get this single peak. These white lines represent the minima of these form factors. As I said, it doesn't change much horizontally, but it changes vertically. So you have this modulated Bragg rod peaks here with peak center at QXY. However, if you tilt it, then two things happened. One is you distort the psi function, meaning you distort the structure factor. So you split the peak from 1 to 2. And the second thing is that the form factor tilted. So that moved the maximum of this Bragg rod peak out of plane. And we'll get to this in more details later. So with this example, we conclude the physics part of the lecture, and I hope you get an idea how to relate the diffraction pattern that you obtain with the structure of the sample, just conceptually, what is the relation. So now we move on to the second part of the lecture, and that's to solve 2D crystal structures from the diffraction pattern. So first, let's see what usually is done to solve a structure in real life. You first get a GID pattern, of course, and then you suggest a 2D crystal structure based on this GID pattern and build a real space lattice. When I say suggest, there are a lot of times the experiences involved. And when you do more, you can guess quickly. If you just started, you need some help. And then from this real space lattice, you build a reciprocal lattice. And use this reciprocal lattice to determine the Bragg peak locations. Those dots are the Bragg peak locations. And index the diffraction peaks with similar indices. So from there, you use those peak values to solve the structure. Many a time, when it comes back to it, you find out it didn't match. So that means the structure you suggested is not correct. So you start over again from 2 to 5. So that's the lecture. This part is concentrated from 2 to 5. So we start with real lattice, real space lattice. We start with this lattice called Bravy lattice in real space. What are Bravy lattices? Well, they're lattices to describe all possible configurations of crystal structures. So in 2D, there are a total of 5 Bravy lattices shown here: oblique, rectangular, centered, rectangular, square, and hexagonal. If you think this is overwhelming, there are 14 in 3D, so we're lucky here. So the purpose of setting up a lattice space such as this one, which is pretty general, is to be able to describe these crystals with this 2D lattice point locations. This R that equals M1A plus N2B. So N1 and N2 are the integers, and A and B are unit vectors. It's more convenient to project this lattice onto this Cartesian coordinates and express it here. So for our work, we'll choose centered rectangular lattice because it's much simpler to deal with. You can see in the Cartesian coordinates, theta equals 90, and your A is along x-axis and B is along y-axis. This is also because it's suitable for most of the samples that our users study. Most of their structures are either hexagonal or distorted hexagonal, occasionally square or rectangle. I should note there that in order to describe a hexagonal lattice with a centered rectangular lattice, you need to include 2 particles in your unit cell. So one is the origin and one is the center. So now we're going to see how to build a real lattice space for a hexagonal packing sample, and how to use this real lattice to build a reciprocal lattice. And I wanted to point it out as a very conveniently the rectangle, the reciprocal lattice is also a hexagon because the Fourier transform hexagon is also a hexagon. So the important thing here is all those dots here represent peak locations Q. Okay, so in order to, well, we already mentioned that we're going to use centered rectangular lattice. So to build a real lattice, all we need to do is to find A and B in terms of this lattice constants. So for a hexagonal, this D spacing D1, D2, and D3 are equal. And there's the small d. And then the center to center spacing is the capital D, which is 2 over square root 3D. Then you will find out A and B. A here is equals to big D, and the B equals 2 small d's. It's easily extended to distorted hexagonals, just D spacings are different, but you can easily substitute different D's in this equation. So moving on to reciprocal lattice now. And we have Bragg diffraction criteria to connect those 2 spaces. And with this simple, this is just a Bragg's law, Bragg diffraction law. And using this one without proof, but you can find out more details from the website, and you have this very simple relationship between the unit vectors in reciprocal space and unit vectors in real space. And immediately you see this very simple but pretty relationship. This is reciprocal relationship A star equals 1 over A, B star equals 1 over B. So I wanted to pause here a little bit for the math and just wanted to point out the implication of this reciprocal relationship. It means that in the real space, if the particles are far apart, because they're big or because they located far apart from each other, then your diffraction peaks are all close together, or vice versa. If your particles are close together, and the spacing will be farther apart. Okay, so if you substitute the A and B into this expression, you get your unit cell all set. Then you'll be able to find the peak locations with this equation, because it's just the geometry here. So for example, we have the first spots here that you just count how many A stars and B stars here. So that's 1, 1, and that's your Miller index. So then your Q11 is 2 pi over D.